Hi everyone. Today a look at acid equilibrium. It's important to note that these kinds of questions are only going to apply to weak acids, where there is a discrepancy between the concentration of the acid itself and the concentration of the hydronium ions. We have this generic equilibrium where HA represents the weak acid itself, such as acetic acid or carbonic acid, a weak acid, somewhere from below that gray bar on the acid-base table, with liquid water in equilibrium with hydronium ions and its conjugate base, A-. We're going to follow traditional equilibrium law rules. It's the products over the reactants, everything to the power of how it was balanced. So we have the two products first, each of them balanced with the 1, so we don't have any exponents here in the numerator, and it's over the HA, the concentration of the original acid, also to the power of 1. Please note, it's quite crucial, we left off the liquid water. We only want to include chemicals that are going to have a concentration in our acid equilibrium expression. It's important to also note that because the hydronium and this A- are in a 1-to-1 ratio, the concentration of the hydronium and the concentration of the conjugate base A- are equal to each other. This means that we can simplify this original acid equilibrium expression to be this. The Ka equals the concentration of the hydronium ions squared over the concentration of Ha. This is the version of the formula that we're going to use to solve for the initial concentration of the acid, the hydronium ions, or even the pH. It's a little bit funny, but this version of the formula is not what we're going to use to solve for Ka itself. Questions that ask us to solve for Ka are actually icebox questions. The thing is, they follow a very regular pattern, and if we're able to recognize that pattern, we can skip the whole icebox. And to this modified version of the formula, where the acid equilibrium constant, Ka, equals 10 to the power of the negative pH squared. Look at that. Before we had the hydronium ions squared, but the hydronium ions are equal to 10 to the power of the negative pH squared. Because it's an icebox, this Ha over here, we need that to be the equilibrium concentration of the weak acid, which turns into the Ha subtract 10 to the power of the negative pH. This is crucial. This is a version of the formula that we can only use when we're specifically being asked to solve for Ka, the acid equilibrium constant. There's this extra move with the subtraction. Yes, we can, of course, complete the full icebox. However, it's such a time-saving, efficient move to use this version of the formula to bypass the process of going through the icebox. In addition to all of this, there's a new concept that we're going to introduce. It's called percent ionization. Here at the percent, it's the hydronium ion concentration over the Ha, where this Ha has got to be the initial concentration. So we don't have this subtraction like we did for the equilibrium. The Ka, the equilibrium constant, is all using equilibrium values in their expression. Whereas the percent has, yes, it has the equilibrium concentration of the hydronium ions, however, the initial concentration of the weak acid itself. There's two really important differences between these two formulas. Here, notice the hydronium ions were squared. Here they are not. Here we had this subtraction, subtract 10 to the power of the negative pH. In the percent ionization calculation, we don't have that move. We also can't forget to multiply by 100. An alternative version of this percent ionization formula is the percent is equal to 10 to the power of the negative pH. Again, notice not squared over the initial concentration of the weak acid Ha, once more multiplied by 100. And I hope that helps.